All right. Greetings, everybody. How are you? It's been a while. Yeah, did you miss me? There's only one correct answer to that. Yes, you missed me desperately. You missed what? You missed my stories. Huh. I've got a good one today. I'm going to save it for a little bit. Actually, maybe I won't. I don't know. So I was sick Tuesday. I'm sorry. Thankfully, that was a quick sickness. My wife was sick last week. Apparently, it attacked me for a little while. And then it went away. And then this morning, I was like, yay, everything is good. I get to go back. Life is good, feel good, ready to go. And then all of a sudden, out of the blue, why doesn't my neck work anymore? You know, one of those where it's just like you moved wrong somehow, and it's like, oh, great, now I'm stuck in one of these positions all day, where it's like, who's behind me? Oh, hello. So slowly but surely that's been working itself out today, but I've kind of felt like a robot most of the day. And looking at an iPad, like it's more, I can't really look down. It's more like a, hey, what's up here, you know? So awkward and terrible, but alas, I'm sure many of you are suffering in your own ways as well. Yes? Yes. So I'll tell you why I think that happened later. When you get to the point of maximum boredom, say, tell us your story. And we'll just stop there for a second and I'll tell you a very terrible story. Sound good? Okay? All right, so let's see. We were in this place dealing with Ohm's law, which we just barely introduced. And we said it's not really a law. It's just how some materials behave. If something is what we call ohmic, if it obeys Ohm's law, it should respond with a graph that looks kind of like this, meaning that I should have a linear graph because I have a linear equation. If I do something like either ramp up the voltage or ramp up the current, one or the other one should respond linearly because there's no squares, there's no inverse functions, there's nothing there that's weird, okay? So you can see in this particular graph, they have plotted I versus V, meaning they're watching the circuit, and as they turn up the voltage, the current corresponds by going up in a linear fashion, okay? That's something that obeys Ohm's law. Something like this does not. When I increase the voltage, I does not increase linearly. Instead, it's some other function, okay? So some things obey Ohm's law, some things don't. In this class, most things will, okay? So you don't have to think about that too much. I just want to make the point that it's not a hard and fast rule that's always obeyed. I also wanted to talk about a few of these points of sort of terminology down below here. For our purposes, keep in mind that when I attach a battery to a circuit, we call it our voltage source. It is the thing that provides potential difference in the circuit. And what it's trying to do is keep that potential difference constant. That's the purpose of the battery. It's like, this is how much potential difference is in the circuit to power the circuit. Okay. What happens then is we may hook up a variety of things in the circuit that provide opposition or resistance in the circuit, and the current is going to vary according to that, just looking back at Ohm's law. V is a constant. If I have more R, I'm going to have less current because less can get through because there's more opposition, and vice versa. All right. We are going to often talk about voltage as being across things, from one point to another in the circuit. It's not something that it's like, hey, at this point, the voltage is a certain value. We're not going to describe things in that way. The reason is because this is a difference. It's a difference in potential between two different points. So we're going to use the term across to indicate like, oh, maybe we're looking at this point in the circuit compared to this point in the circuit, and across those two regions, what's the difference in potential, okay? On the other hand, we will talk about current as passing through different things. So voltage is being across things because it's a difference. Current literally goes through parts of the circuit. And we'll talk about how much current is passing through different things in the circuit. And then finally, please don't get confused thinking like a battery is like a water tank and it's like full of charge. And all I'm going to do is like pour the charge into the circuit. And then once I've poured all the charge into the circuit, the battery is empty and everything is gone. It doesn't work that way. Instead, there is charge everywhere in the circuit. I just need to give the charge a reason to move. And all of the charge everywhere goes around the circuit. None is being used up, none is being produced. We're just taking all the charge that already exists in those conductors and we're just making it flow in a loop, okay? So don't get this idea that it's something that we can consume or something that we can create. We're just giving the charges a reason to move, and the way we do that is with voltage. We're essentially creating a higher voltage and a lower voltage, which just like with gravity, if there's two different heights, things want to go from high to low. We're creating that potential difference, which makes the charge want to move. So, a brief side point before carrying this a little further. In lab, you're actually going to play with resistors, just like you will play with capacitors and other circuit devices. Resistors generally kind of look something like this, a little tube. They're generally colored in some way. They have these little stripes of color. I just want to make sure that all of you understand how to look at those stripes and tell what the value of the resistance is for that particular resistor, okay? So you will notice there are 4 different stripes and they all use this particular color code. So what you want to do is look at the first two color stripes and see what colors they are. And they tell you the first 2 digits. So in this particular case, we have red and green, which we can look over here. So red is a 2 and green is a 5. So we know the number starts with 2 and 5. Looking at the third one, it says is the multiplier. And it's going to tell you times 10 to the what, okay? So here, our third one is yellow. So yellow, you can see in our diagram, corresponds to times 10 to the 4th. So you can put that down. And then the last one is the tolerance. It's basically the uncertainty. What range does the value actually fall within? So you can see we have a silver band there, which says 10%. So this is 25 times 10 to the 4th, plus or minus 10% of that value, okay? Which is really quite a large range of resistance, okay? So if you're wondering, well, how do you know the bands don't go the other direction? Well, if you see, say, a silver or a gold as the band there at the end, notice they only exist here once and they don't correspond to a number. They only correspond to a tolerance. So the end that has the silver or gold band on it is the last one. That's the 4th one. You want to start from the other end, okay? Does anybody have any questions about that? I think that's probably one of the more straightforward things we do in this class. Maybe a little bit. You're good. So when you get to lab and they're like, hey, find the 5,000 resistor, you're going to look through the pile and be like, oh, which colors correspond to give me that particular value, okay? Let me go back a slide. I'm trying to remember if I told you. I don't think I gave you a unit for resistance, did I? Huh. We should talk about that. The unit is surprisingly the ohm. It is Ohm's law, all right? So the unit of the resistance is the ohm, and we represent that with a Greek letter that I find difficult to draw, which is, what is that, a sigma? Is that right? Omega. That is omega, yes. I'm getting my own numbers or letters confused. And I often don't draw it even that neatly. I just go, ugh. And then later it just turns into ugh, like that, you know, and it just gets worse and worse, okay? So just keep in mind that the unit is ohms, and we use the omega symbol to represent that, okay? So let's see, we have Ohm's law, we talked about resistors, which means we have to talk about something called resistivity, which is a confusing word to say, I think. We look at the word and you're like, resist, it's like it just kind of keeps going. You want to pronounce it one way at the start, and then the next thing you know, it's like gone somewhere else, and you're like, maybe I should have started that word differently, okay? So it's resistivity. This is related to resistance, but it's slightly different. And it turns out I find this kind of hard to explain, which means if I find it hard to explain, you find it hard to understand, probably. Okay, so I'm going to try, and then you're going to look at me, and then I'm going to do it again, and then you're going to look at me some more, and I'm going to explain it again, and you're going to be like, I kind of see what he's driving at. Okay, so bear with me here for a second. Let me start by giving you the equation that tells us how it relates to resistance. So resistance is R, and R is equal to rho, which is the resistivity, times L divided by A. L is the length of the material, and A is the cross-sectional area of the material. Resistivity times the length of your material divided by the cross-sectional area of the material tells me the resistance of that piece of material. So let's see how to describe this best. Okay. First of all, let's say that we have a piece of material. Let's pretend for a second that this is a segment of wire. Okay. See, it has a cross-sectional area. That's a circle, etc. Let's say we've just sort of zoomed in on this wire, and maybe this is made of solid copper. Okay, got that? Everybody's good there? Copper is a conductor, so it has relatively low resistance, but there's still some. And you might imagine that if my wire is this shape and size, there's a certain value of resistance, but if I made it twice as long, and maybe I made it like thicker, well, clearly it's going to offer a different amount of resistance to charges going through it because there's a different amount of stuff, okay? Would you agree that that makes a little bit of sense, first of all, okay? So what we're going to say is this thing that is the resistivity is like a property of copper itself that has nothing to do with how much of it I have or what size of a chunk of copper I'm using. It is an intrinsic property of the material. We say that copper has a certain value of resistivity. Okay? By itself, that doesn't tell me how much resistance it's going to offer. It's just a property of the material. What I can then do once I have that value is I can multiply it by how long a piece of copper I have and divide by the cross-sectional area of that copper, and it will take that intrinsic number for copper and transform it into how much resistance this particular chunk of copper is going to put up in the circuit. Do you see the difference between those two a little bit? Okay? So resistance is about a particular piece of copper that's a particular size and shape and how much resistance it gives. Resistivity is about the element copper itself. Okay? It is something about how much opposition in general the element copper will put up in a circuit, okay? One is intrinsic to the material, one is about a particular piece of material and how much you have. Do I need to explain any part of that again? You get the idea? Okay, so let's look at this equation. Notice, first of all, length is in the numerator, okay? So if I have a longer piece of material, we get more resistance. I think that makes sense, right? It's like you can imagine if you're an electron and it's like, I need to go through this piece of copper. And maybe the copper is only 1 meter long. You're like, okay, and you bounce your way through that piece. But if the copper is 2 meters long, you're like, I've got to do that twice. There's going to be more opposition if I have to go through twice the length of wire as opposed to just half of that, okay? On the other hand, notice what's happening with the cross-sectional area. If the area is smaller, we get more resistance. If the area is smaller, so if I take the cross-sectional area and make it crunch down, there's more resistance, okay? Think about driving on a highway. You've got 6 lanes, right? Cars are like, whee, here we go. And then all of a sudden 5 lanes are blocked, right? And now everybody's like, oh man, we've all got to cram into this tiny little area and fit through. It doesn't go so well, right? All of a sudden, the highway, just by becoming more narrow, offers more opposition to those cars being able to get through. That's essentially what happens here. If you take the wire and make it smaller in cross-sectional area, it offers more opposition to the electrons, to the charge being able to flow through, okay? So more length, more resistance, smaller cross-sectional size, more resistance. Got it? Yes? Are you alive? Is anybody okay out there? Hello? Everybody wake up. See, if you don't wake up, then I'm going to make you all stand. We're just going to stand for the rest of class. How's that? No? Push-ups? Jumping jacks. This isn't PE. Yeah, well, and then we'll all hit the showers. It'll be great. It's fantastic. No. What a stupid idea that is, right? Like PE, like in the middle of a school day, right? It's like, you go to class, you go to class, you go to class, then you get all sweaty, and then you go to class, and you go to, I don't know. That makes no sense. High school was weird, right? And I don't think I can do jumping jacks today because my arms and back and neck don't work quite right. So you do jumping jacks, I'll watch while we all wake up. Yeah, that's not going to happen, right? I should get like a whistle. And be like, yeah, double time! And, more jump, No, that's not going to work for anybody. All right, so let's look back at this. Let's see, we talked about that. I don't really want to talk about that too much or that too much. I do want to mention this, though, okay? This is simply the reciprocal of resistivity. Conductivity, we use sigma, and it's equal to 1 over rho. And instead of being a measurement of how much opposition, it tells you how well an object conducts. Okay, so it's just the exact opposite property. We should talk about some units real quick. The unit of resistivity is ohms times meters. So it's the ohm meter. And the unit down here is the reciprocal of that. So we could say it's ohm meters to the minus 1. Or 1 over ohm meters. Resistance, resistivity, Ohm's law. We're going to use all this a little bit more in the next chapter. But before we can get to any of that, I beg you to answer this question the right way. Otherwise, we might have many more things to talk about. We've got a battery. It has a positive side. It's going to have a negative side on the other end, a wire, and a light bulb. Remember, if I'm going to make charges flow, I have to give them a path that's conducting, and it has to be a closed loop. It can't just be like, go over there. Instead, I have to give it a loop that goes all the way around. You remember that diagram of the man that was dumping the water in the top, and the water goes around, and I pick it up again? I have to give it a closed loop. In which one of these have I provided a conducting path, and there's a complete loop that has a high potential and a low potential inside of it? While you're thinking about that, I'm going to make a little list here. Say, for current to flow, we need a conducting path, and we need a closed loop, and we need a potential difference. So these two are, we'll say, a place to go and a reason to go. We have to give the charges a place to go and a reason to go. So which one is it? And it's looking a whole lot like 3, okay? So you might imagine that positive charges start here and they're like, whee, look at that, light bulb. And technically they would like go up in here and work their way around, and then come back out the wire, and then try to find their way down to where there's negative potential. And then inside here is that man that's like, lifting up the buckets of water, doing work on the charges, raising them to a higher potential. Actually, that's where our magical chemical reaction is that's doing work to raise the charges to a higher potential. And then off they go again, essentially falling back to the low potential, all right? So the correct way to light a light bulb is number 3. If I double the voltage across a conductor and observe that the current increases 3 times, which one of those things can you conclude? We doubled one and got triple of the other. Who says 1, 2, 3, 2, 1, 4, 6, 9. No, I'm done with that. Yeah, which one? 5? Yeah, I don't think so. So number 2, Ohm's law is not obeyed. If I double a thing and the other one doesn't double, well then that's a non-linear relationship. Ohm's law is not behaved in this particular situation, okay? Let's see. I'll give you a second to think about this one. Talk amongst yourselves. Ask your friends. See if anyone can give you an answer. I'll come over here and bother you too. I don't know why. I'm just going to stand here. No pressure. No pressure. No pressure. No pressure. What's the answer? What do you think? Any votes out there? I see votes for 2, 5, 4, 5, 4. Okay, so which one is it? I need to get a 4 over here, right? I need 4 times the resistance. How do I get that? I need a 4 in the denominator of the denominator, right? I need a 4 down here. How do I get that with the squared? Oh, r over 2 squared would be enough to do that. So that means the diameter is half. Yeah, it was 4. Good job. I appreciate the vote at the end. Yeah, I think you already said 4 perhaps. Yeah. So let's see. It says that we have the same metal. That implies the same resistivity. We have the same length, so that's the same. But the resistance of one of them is 4 times the other. The only place that can be coming from is this area getting smaller. So the way I could get that area smaller, and well, the diameter and radius is going to change by the same amount. One's just half of the other, okay? So if this area is pi r squared, by dividing the area by 2 and then squaring that gets me a 4 up here, okay? Anyone else? Yes? The area is divided by 4, but that just means the diameter would be divided by 2. Half the diameter is 1/4 of the area.
L over R over 4, R squared over 4. You move it to the other place, or
If I move it to the other side, yeah, same thing. No, yes, no. Take a look at it and let me know if it's not clicking a little later, okay? Next one, or is there a next one? Same kind of idea. We're playing with the same equation. So take a look at this and see if you get the answer. L over A, once again. So, twice the length. We're stretching this out to twice the length. The volume is going to stay the same. So if it gets twice as long, the area is being cut in half, okay? And then I'm gonna have the same length times area to get the same volume. So if that's true, take a look at what's happening now. I've got a 2 in the numerator, and then this is going to give me another 2 in the numerator, which means it increases by a factor of 4. Okay, it increases by a factor of 4 if I double the length and halve the area. Yeah.
So why is the area cut in half again?
The area is cut in half in order to keep the volume constant. So the volume of this, you might imagine, if we have like a cylinder, okay, the volume of this is the area times the length. So if I double one and halve the other, then I still have the same volume. Okay, so 2L results in A over 2, and then I still have A times L. Okay. Anyone else? All right. Which brings us to this. I'm going to go ahead and say that the last little bit of this chapter, there's 2 things we're going to do. I want to talk a little bit about just like electricity in general before we move forward. And then we're going to talk a little bit about how fast electrons move, and then we're going to move to the new chapter. But probably before I go to the new chapter, I'm going to tell you what hurt my neck. And then you're going to laugh at me, and then you're going to laugh at me some more, and then I'm just going to start the next chapter while you're still laughing. Sound good? Seems reasonable? Okay. So, a couple of different things here, first of all. Electricity is fantastic. It's fantastic, first of all, because we can generate it in one place and then transfer it to another place. We can store it, and we can also convert it into other types of energy, okay? So it would be kind of terrible if, I had to somehow like manually light up the screen. That sounds like an awful thing to have to do. I don't even know how I would do that. Like screens were like I had to make a fire and like physically make the light and make it shine through the back of the screen, which like that provided a backlight, and that would just be absolutely terrible. Instead, if I want energy from light, well, I can take electrical energy and do a conversion. I can take electrical energy that was produced hundreds of miles from here, perhaps, that was transferred here in the form of electricity, stored in a battery, and then converted into another form, okay? If I wanted to, I could take that and convert it into like mechanical energy in the form of a motor, right? I could take electricity and make it actually physically move or turn something. Well, that's kind of fantastic. I could, like I said, generate light. We could take electricity and pass it through a heater and have it generate heat. So we can take electrical energy, convert it in other forms. It could have been stored along the way, and that just makes it incredibly useful. The point of this slide is I want to give you some equations for power, and we're specifically talking about electrical power here. Power is equal to the current, which is something we know about, times V, the potential difference. And I'm about to do something that should seem familiar to you. Now keep in mind, there's some other quantities like resistance that's involved too. So I could use Ohm's law and rewrite this another way. So I could plug in IR for the voltage, and then all of a sudden I have an alternate form of this equation, which is I times IR, which is I squared R. Or we could do this one more time, and I could maybe plug in for here. I could say this is V over R. And if I do that, we're going to get V over R times V, which is V squared over R. Three different forms of the equation based on which of the three variables you happen to have available to you. Power. If I want to find out how much electrical energy I'm using, that is in general equal to power times time. You could use any of these power equations and then multiply it by how much time you've been using that. Take a quick look at what the units are. So in general, power is in units of watts, and at least in the units that we use in physics, time would be in seconds, okay? But I could, of course, convert those as well to another version of power and another version of time, which might be in a form that you've seen before. So if instead I converted this into kilowatts, and instead of seconds I used hours, maybe if any of you have ever paid a power bill before, you've seen that you pay for kilowatt hours. Kilowatt hours is directly a unit of energy. It's literally how much energy you are consuming when you pay something in units of kilowatt hours. It's the electrical power times how much time you used that power for. Okay? So how does that work in your house? We're not going to talk so much about how it works, but more about how it fails, just to keep you all just a smidge safer, okay? So we know that wires, like we said, like copper, it's not a lot of resistance, but even so, like even in copper, there's free electrons, but there's all these nuclei in there that they keep colliding into. So there's still some resistance. So if I take a house or a large building like this and have many meters of wire, all that little bit of resistance starts to add up, okay? And that means that as the resistance adds up, we could start to see this power equation, which is I squared R. As I increase the current, that resistance also comes into play, and then power can be produced by the wires. This is usually in the form of heat. Why is it in the form of heat? Collisions. As I pass more and more electrons through those wires, and they have more and more collisions with other electrons and with the nuclei of the atoms, every one of those collisions is some type of a loss of energy. That energy has to go somewhere. It generates heat. Well, if those wires start to heat up because there's too much current, well, things start to happen, right? Bad things can start to happen. If everything is put together properly, maybe you're kept safe, but what if all of a sudden one of those wires starts to melt the insulator around it, and that happens to be sitting next to, I don't know, a piece of paper. And now all of a sudden you're like, why is there a piece of paper in my wall? I don't know how it got there. That's your fault, okay? But then it catches the paper on fire, and then the wood catches on fire, and then life is terrible. But thankfully, there are things to keep you safe in the house, either in the forms of fuses or circuit breakers. What both of these devices do is simply open the circuit. They literally make the conducting path not exist anymore. Remember, we need a closed loop for the charges to flow. All they do is say, let's cut a hole in that loop so that charges can't flow anymore. So even though it's like all of a sudden current is getting really, really high, and it's like, oh, a fire might be about to start, at a certain point, these devices are in there to say, if the current gets to this level, let's just manually make the circuit not be complete anymore. And then all the charges are like, nowhere to go. I guess I'll just stay here. Nowhere to flow to. And all the current stops. So a fuse literally looks something like one of these devices. I'm going to look at this one in particular. Basically, you take this little apparatus and connect a wire to one side and connect a wire to the other side. Current's flowing through there. And if the current gets too high, this little piece of metal inside melts. It's a physical way to make basically part of your circuit safely just go away. And then all of a sudden, if that melts, well, there's no connection between these two wires on the end. The current can't go through anymore. So that's kind of nice, okay? That's an example of a fuse. A circuit breaker is those little things behind the little gray box in your apartment somewhere where occasionally you hear ch-chung, and you're like, hey, why'd the lights go out? And then you go into the little box and you're like, oh, this one's not in the same direction as all the other ones. And you go, ch-chung, and then you're like, oh, the lights came back on. That's fantastic, okay? You do this all the time probably, especially if you have roommates. And then your roommates are simultaneously like using the microwave, and someone is using like a hair dryer, and someone else is making toast. And toast is great, isn't it? Does anybody hate toast? Toast is the best. Who doesn't like toast? It's simple, it's nice, you can put anything on it. It's amazing, like you take a piece of bread that's all like floppy, and then you heat it up a little bit, and now it's all tasty and crunchy. What an amazing thing, toast. So you're doing all this stuff at the exact same time, right? Every one of those devices you turn on are like, I need some current to do my work. I need some current. They're all like, give me more current, give me more current. So the current that's passing through your walls is getting higher and higher and higher. At some point, that physical device is set in such a way that if the current gets to a certain level, well, again, this time nothing's going to melt, but a piece of metal in here literally bends a little bit. And when that happens, it pushes this little piece down and creates a little gap in the wire. So that again, it's like just like with the fuse, it literally puts a break in there. So the charges are like, fine, got nowhere to go. There's no complete closed loop anymore, okay? Here's what you don't want to do. Probably you've done this over and over and over and over again, right? You've got all you and your roommates have all the things turned on, the lights go out. You go back, you push the switch back. You go back to doing all your things again, and the lights go out. You go back to doing all your things again, the lights go out. And then maybe one of you gets a bright idea that's not so bright at all. And you go and you look at the little devices that are behind the little gray door, and you look at them and they have numbers on them, and maybe one of them says 40. And you're like, I'm going to Home Depot. And I'm going to find one of these little things that looks exactly like this, except it says 50. Because I bet 50 is better than 40. Right? And then you go and you do that, and then you put that in the thing, and you're like, everything stays on all the time until your house burns down. So, kind of think about those things just a little bit. That 40 on there probably stands for 40 amps, which means that if the current gets to 40 amps, I'm going to shut it all down because I know that 41 amps or 45 amps or 50 amps in this construction could start a fire. So it's trying to keep you safe. So don't get any ridiculously unbright ideas by trying to put in a higher rated circuit breaker or fuse. What you want to do is go look elsewhere. If the thing keeps turning itself off, there's a reason. It's not just like somebody put in 40s instead of 50s. No, the 40s are there for a reason, okay? Instead, it could be exactly what you expect. It could be too many. Turn one of them off. Like, go plug one of them into a completely separate part of the house, so maybe it's on a different loop and it will be having its own current separately, okay? So maybe just try not to do all of those things at the exact same time. Or something's wrong with one of them, and it's asking for more current than it was originally designed for. How many of you have a hair dryer that smells a little bit like smoke? Just admit it. Like you've probably, or maybe you've got some device and you're like, when I turn this thing on, it smells a little like fire, but I've never seen a fire, so it's probably fine, not a problem. That same device, ask yourself, how many times have you dropped it? Ah ha ha ha, right? What's probably happened in that device, especially something like a hairdryer because it's just too simple for it to happen, is that instead of it being built like it's supposed to be inside, maybe there's a wire that has come loose and it's touching a part that allows the current to sort of just bypass what it's supposed to do. And now all of a sudden it's like, I'm missing part of my current. I need more. Where's my current? I need more. Where's my current? I need more. And it keeps requesting more to try to do its work. And all of a sudden the current's going higher and higher and higher. Something's broken. Okay? So if something smells a little like fire, it's probably not your hair. It's probably the device. Replace it. They're like $8. You're like, no, I have a nice hair dryer. Mine was 140. Replace it. 140 versus your apartment burns down. Or just have wet hair. Like whatever it takes. Stop using that thing. Okay? So there's either too many devices, don't use as many, or if you notice that something seems a little weird with one of them, like fire, replace it. Okay? Also, the thing that smells a little like fire, do you ever touch it and get just a little tingle? You're just kind of like, ooh, what's wrong with that, I wonder? Oh, I'm sure that's fine. That's not a problem at all. You're probably getting shocked. Replace it. Okay? So no one's going to die from a house fire that was caused by electrical faults, right? You have a question? Or you're volunteering to die from an electrical fire? Okay, good.
If somebody's plugged into an outlet, is it currently sucking out like current, or is it stagnant?
There's some debate on that, and it depends on the device. The best answer to that is, in general, if so, not much at all. So typically there is some sort of switch inside that's literally keeping the circuit open so that the charges have no reason to go into that device to begin with. But that's not to say there's not some charge flowing through some part of it still, especially if it has some little part broken. It could be drawing current and you're not aware. Anyone else? Stay out of Home Depot. Okay? Please, just don't do things. Okay? Let's see. What else did we want to talk about here? First of all, years ago, about 20 years ago, I was lying in bed. And this is when I first discovered I was an idiot. Okay? You're like, oh, I've known that forever. Like, okay. Or maybe you've discovered you're an idiot in advance of me. So congratulations on figuring that out. So I'm lying in bed. What do you do when you're in bed? Like, it's cold or something. Like you got the blankets all wrapped around you. Everything is happy, And for whatever reason, I decide, I think it's time to roll over. At some point you're just like, I'm sick of lying on this side. I want to lie on the other side. So it's like, here we go. Woo, roll over. What I didn't realize is I was right on the edge of the bed. You know what I'm saying? Like, I'm like lying right here facing that direction, and I decide it's time to roll over. So I roll over, and I'm like, uh-oh, we're in empty space now. Something's happening. So immediately you want to get your arms out, your legs out, something to brace yourself. I was all wrapped up in the covers. Right? That didn't fare so well. I couldn't get anything out, nothing out. So I hit the floor, but the thing that hit first was my head. Right? So like I kind of landed, it's like head first, and then the rest of the body hits, right? So it's like crunch, and then I hit the floor, and I'm thinking like, I'm gonna be paralyzed, and I'm an idiot, because what a dumb way to get hurt. So I lie there for a second thinking like, oh, everything still moves. Like, oh, I'm actually not hurt. But alas, now, occasionally, out of the blue, it'd just be like, something's not right. I'm convinced that day, because I never had back problems before that, but after that, a couple times a year, it's like, oh, and then I'm left all stiff for a couple of days for no apparent reason. Would you agree that that's probably where I hurt myself? It's the only injury I've had that even remotely seemed to be a neck injury. So, yeah, be careful. Beds are dangerous. Very dangerous. Now, a little while after that, and this is the one that everyone laughs at me for, I injured my back again, which I think this injury only came because of the first one. The first one is like physical damage, right? The second one, it was just like I needed to sniff, right? It's like, maybe your nose is running a little bit and you're just like that. I did that and I went, ah! And everyone's like, what's wrong with your back? I sniffed. They're like, you hurt your back sniffing? Like nobody can hurt their, sniff right now. Tell me your back muscles don't tense a little when you do it. Do it. No, not at all. I can't do it because when I do it, my back hurts in the exact place where it started hurting this morning. So clearly there is a connection there. I'm like, don't try it, really hard. You feel that in your back? No? Okay, see, I'm an idiot. And you can laugh at me for the rest of eternity. That's totally fine, all right? Back hurts though. Please, does anybody have any magic tools or anything?
Advil.
Advil?
Excedrin.
Excedrin. Well, which one? Both. I think it's not both. Wait a minute, let's see. Excedrin.
Here.
No, you can take those together, can't you? I think Excedrin is a different drug. Ibuprofen is Advil. And you can, yeah. It's Tylenol you can't take too much of. Tylenol's like 2's okay, and then 3's on the verge of something, and then 4 you die. Or something along those lines. Tylenol's terrible. No. You think that's what needs to happen? Yeah. I don't like the sound of that. It's like, just relax. Yeah. Crunch. Yeah, that's not how it works.
That's how I usually work.
Yeah. I feel like I need to fall out of the other side of the bed. I need to do the exact opposite to reverse the chiropractor. Land feet first next time. Well, how's that going to help my neck? Okay, so
It's in reverse. It's like how you went neck first, now you went feet first.
yeah.
So it'll even it out.
Okay, so I think what's going to happen is at some point this evening, my wife is going to be in another part of the house and be like, what is the noise? And she's going to come in and be like, why are you throwing yourself out of bed? What is happening? Brother, my class told me to. Like, you're going to listen to college students. Like, yeah, I didn't have any ideas. This seemed to be pretty good. They also told me to go to Home Depot and get a number 50 and just connect myself to that and see what happens. All right, so let's finish up this chapter, and we'll see where that gets us. Everything we've been talking about in this chapter, and what we're going to talk about in the next chapter, and probably the next chapter, and the next chapter after that, is something known as direct current. Direct current. We're going to keep things sort of on the easier side in this class. That's a bit of a laugh, I think, because a lot of things we've done have been hard. But when it comes to dealing with types of current, alternating current, this other kind, is a whole lot more complicated to deal with than direct current. But we can learn a whole lot from direct current. In the case of direct current, it looks just like this. There's a value, and it just stays that value the entire time. That's pretty simple, right? It's just like, there's the current. That's what it is. Don't worry about it changing. It's going to be that for the whole problem. Okay? That is, on the other hand, not what comes out of these outlets on the wall. Okay, so it's like, okay, it's good. We can use it. You can do a lot of lab experiments with it. A lot of things run off of direct current, but that's not what we get out of the wall. So anything that uses direct current, we have to do a conversion before we actually connect it to a device. So what's coming out of the wall is what's known as alternating current, and it does something like this, which is a little bit confusing because we could say that both the magnitude and the direction are ever changing. The magnitude and the direction of the current are ever changing. So take a look at that graph, first of all, and let's look at maybe this first portion between the green lines. Notice those are all positive values, but they're different positive values. So at the starting time, there's no current, and then there's more current, more current, more current, more current, more current, a maximum current, and then less, 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 and less. But all of these are positive, meaning that current was flowing in one direction that we call the positive direction the entire time. It just increased in how much current there was and then decreased in how much there was all in the same direction. But then, between these next 2 points, notice here it's all negative. So it flips directions and gets more and more and more and more and more and less and less and less and less in that opposite direction. And then it does the same thing back in the original direction, back and forth. It's almost like all of this charge it's almost like a pendulum, right? You think of how like a pendulum swings, it's like kind of stopped, and it speeds up, and then slows down. It's kind of like that's what the charges are doing, except they're all flowing one way faster and faster, and then slowing down, and then speeding up the other way, and then slowing down. And they're doing this thing rapidly. Okay, they're all going one way, and then all going the other way, and then back and forth, and back and forth, and back and forth. It turns out that at least in this country, it will say switches directions. I can't write. 60 times per second. And that's what's known as the frequency, which is 60 hertz. In other countries, it's 50, which is why if you go to Europe, you can't just plug your stuff in directly. You need a different charger to connect to the different outlets, and it's not just that the prongs and the physical connector is different. It's probably different just to make sure you can't plug it directly in and just destroy everything. You actually need a conversion because there it's alternating directions less often than it is here in the United States. So this sloshing or swishing back and forth 60 times every second, all those charges are changing directions. Yeah.
Isn't the other reason because there's a voltage difference?
There is a voltage difference as well. Yeah. It's like just all different. Why we all can't get on the same page, I don't know. As far as I understand, there's no technical reason other than just someone decades ago said, let's do 50. Let's do 60. Why aren't we what?
On the metric system.
Why aren't we on the metric system? Because this country is dumb. At least that's how I see it. So I don't know. We should be. Now I'm sad. Why? Also 60 versus 50. 50 is just nicer, right? You know, who in the world knows? Okay. So I just want to introduce to you at this point, like that's what alternating current is. We're going to spend a chapter on it later in the semester, assuming there's time. I just want you to be aware that it's different than what we're going to be talking about most of the semester, okay? So that's alternating current. The last thing that I want to do in this particular chapter is a quick calculation. We're not going to do this derivation, but you might remember we talked about kind of this diagram on the top right, how we talk about positive charges moving through as current because everything in electricity is based on positive charges, when it's actually electrons that are going the opposite way, and they're not just like a fluid that's flowing. Instead, they want to go that direction, but they end up doing this bouncing around sort of thing and sort of just kind of eventually making their way that direction, right? It turns out that they have a velocity that we call the drift velocity. And we call it a drift velocity because that's kind of what they're doing. They're not just saying like, oh, time to go this way, here we go. Yay, we went this way. No, they're just sort of like, oh, I'd very much like to go that way. Yeah, I'm going to hurt my neck again, right? And then we just sort of drift over this direction as best as we can considering all these collisions that are going to happen along the way, okay? I want to give you some feel for what that drift velocity is. And it turns out that if we have a copper wire, and let's say that it has a cross-sectional area of 0.5 millimeters squared, so a wire, it's a small wire, and we decide to pass a current through it of 5 amps. You don't need to know the equation or how to calculate it. I can just tell you that the drift velocity in this particular case is 0.00735 meters per second. That's 0.735 millimeters every second. 3/4 of a millimeter every second. Okay? So keep in mind, you hit the light switch over there. Remember we talked about you don't have to like wait for the electrons to like get up here and light things. Imagine if you did have to wait. It'd be like, all right, we've got class in a week. Somebody should turn on the lights. And then a week later, it's like, oh, yay, the electrons got there. We have light. That's fantastic. Okay? Instead, remember, they're all moving at the same time. What happens when you flip the light switch is that electric field happens everywhere, and it says, okay, electrons everywhere in the circuit, time to go. And then they all start just very, very slowly working their way around the circuit. So we think of electricity as like this thing that's like, ooh, it flows really, really fast. Not really. It flows really, 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 really slow. It's electric fields that happen really, really fast. Okay? So it's like the instruction happens fast. The actual movement is really, really slow. Got it? Next chapter. Next chapter, just for a little bit. Okay? Just for a little bit, chapter 28. Let me say a couple of things. Homework, your chapter 20, whatever it was, 6, the one about capacitors. Instead of being due tonight, I bumped that to Saturday night since I was out earlier in the week to give you a little bit more time and a chance to talk to me if you needed to. We're going to try to keep up the pace of having an assignment due 1 week after we finish the material. So we just finished chapter 27, so that means I'll be opening up an assignment due about a week from now. Since it's not there already, we will say, what is today's date? Today's Thursday?
Yeah.
Maybe we'll say like a week from tomorrow, just to give you 8 days instead of 7, okay? And then chapter 28 will be due a week after we finish all of that, all right? Also, our next exam is going to be on the 15th, so we have 3 weeks from today. 15th, yes. 3 weeks from today, not like next week, we still have 3 weeks. I know it seems like already, but it's been like 3 weeks, I think. And it's going to be another 3. We're just like halfway in between them right now. So I just want you to be aware of that. It was supposed to be a little sooner, but I decided to bump it back a little to give us some more time. So in chapter 28, we are going to talk a little bit more about circuits. We dealt with capacitors in circuits. In this particular chapter, we're going to focus on resistors, now that we know what they are. So first of all, as a source of review, our circuit elements and the symbols that we use up here on the top right. Keep in mind, the battery is represented by 2 lines, one longer than the other one. The longer one we consider to be the positive side of the battery. We're going to say that that's the side where the current originates. That's the side at higher potential. A capacitor is just 2 equal length lines, or one of them could be curved, but we're not going to use that terminology much. A resistor, we use like a little squiggly sort of line, which if you think about it is an exact diagram of opposition, right? You can imagine if charges would like to go through there. A straight path is easier than like, oh man, I've got to make all these little turns. They're not actually making little turns. Don't get that idea, okay? But it represents some opposition to current and charges being able to get through there. For a wire, we'll just use a straight line. For a switch, we have a little thing that's a broken line. You can imagine I could take that line and make a connection again. And then for ground, which we're going to talk a little bit more about at a later date, we use sort of this series of decreasing length lines. And once again, you can think of ground as a location where the potential is equal to 0. It's like the lowest potential in your circuit. And typically, it means you're literally connected to the earth. You're connected to what we call ground. So, first of all, before we get to the next slide where we deal with some resistors, let's talk a little bit more about the battery. So remember, the battery is trying to provide a constant voltage, a constant potential difference. But it's going to fail a little bit. It's not going to be perfect at it. Have you ever, I don't know, connected a battery to something that actually like measures what the potential difference is, what the voltage is? And you look at the battery and you're like, 12 volts. I bought a 12 volt battery. Fantastic. And then you make a connection and actually put it in a circuit and you see how much it's actually producing, and it's like 11.79. And you're like, I bought a 12. Why is it 11.79? And then after a little while, you kind of get over it and be like, I guess there's some uncertainties and stuff, whatever, it's fine. It says 12, I guess that's as good as they can do. Well, it turns out it's still a 12-volt battery, okay? The thing is that is the constant it's trying to provide, but it's going to fail a little bit because of what we call internal resistance. This is resistance that is inside the battery when current flows through it. Inside the battery, there's a mess inside the battery. There's that chemical reaction. There's that little man that's like moving charges, you know. There's some opposition inside the battery itself. Well, that opposition doesn't come into play unless I make a connection and actually try to send current through the battery. When it's just sitting there not connected to anything, it's 12 volts. As soon as I try to pass current through the battery, a little bit of my voltage gets eaten up by that resistance that's hiding on the inside of the battery, okay? So we are, in general, going to ignore this. I just want you to be aware that it's there. You could have a homework problem that says, hey, I have a 12-volt battery. When I make a connection and pass this much current through it, it reads 11.5. How much is the internal resistance? Once we analyze how to deal with circuits, that should be something that you're able to do. So at this point, I just want you to be aware that there is an internal resistance that happens, which brings us to the point of this particular chapter. We did capacitors in series and parallel. We're going to do resistors in series and parallel as well. The idea of series and the idea of parallel is exactly the same. The fact that series means they're connected where you go through a resistor and then you're like, oh, I've got no choice. I have to go through the next one. They're one right after the other. That's what we mean by series, okay? So you can see that illustrated on the top right. We've got 3 resistors that are connected in series to each other and connected to a battery. So you can imagine if my positive charges leave this side of the battery, the positive charge, they make a current that goes around this way, and the current has to pass through this resistor, and then it says, oh, great, I'm done with that resistor. Oh no, there's another one, I have to go through it. And then I'm done with that one, and then, oh no, I have to go through resistor 3 before I finish making the complete loop. Resistors 1, 2, and 3 are in series with each other. So here are the rules for series resistors. Series resistors all have the same current passing through them. However, they may have different potential difference across each of them. Same I, different V. Same I, different V. If you can remember what's happening with the current, you can keep these rules straight in your head. Just go back and think about what we mean by series and think about the current. Think about being a charge that's flowing around this way. It's like if a charge goes through this first one, it has to go through the second one, and it has to go through the third one. None of the current can go anywhere else, which means that all of that current has to pass through each one of them, and it has to be the same because there's no other option for the charges to go anywhere else. So they all have the same current, but may have a different voltage across them. So we can do something like this. We can say that the total voltage is equal to the voltage across resistor 1 plus the voltage across resistor 2 plus the voltage across the resistor 3. The total is what's being provided by the battery itself, And it has to be equal to the potential differences across each one of them in series added together. And I can use Ohm's law to re-express this. V total is also equal to the current times resistor 1 plus the current times resistor 2 plus the current times resistor 3. I don't need a subscript on the current because they're all the same. And V equals IR for each one of them. So we applied Ohm's law 3 different times for the 3 resistors. Then I can factor out the current. So it's the same I everywhere times R1 plus R2 plus R3. And this particular combination of resistors is the equivalent resistance, okay? I could take all 3 of those and just add them up and replace them with one resistor with that value and get the exact same effect, okay? Just like we did with capacitors. Just notice this time the adding is in series instead of in parallel. So it's exactly backwards. So when I'm dealing with series resistors, we can find the equivalent resistance by simply adding them together. So keep in mind, the more you put in series gives you more resistance. And I think that makes a little bit of sense, right? Remember we said if I had a longer piece of material or I had more distance for the charges to have to pass through and deal with all those collisions, there's going to be more resistance. This is kind of the same thing, right? It's like I took a resistor that has a length, and I took another one, which gives it more length, and I took another one, which gives it more it has to pass through. There's more resistance if I put one right after the other, okay? More resistance if I put more in series. Which brings me to these 2 questions, and then we're going to be done for the day and for the week. Assume that the voltage of the battery is 9 volts and the 3 resistors are exactly identical. What is the potential difference across each one? Don't think too long. What do you think? Yeah, they each have to be 3. I need 3 and 3 and 3 to give me a total of 9, okay? So we said that they may have a different voltage. They have a different voltage if they have a different resistance. Here they're all identical, so they all have the same voltage. Which brings us to this. What is the voltage across R1? And I will step you through this. First of all, those are in series, which means I can just add them. Okay, so we can add those, and we know that the total resistance or the equivalent resistance is 6 ohms. I can then use Ohm's law. V equals IR. And you could potentially jump to this answer just by kind of looking at the numbers, but it's okay if you can't, that's fine as well. And we can say that this is going to be 12 divided by 6 gives me I total. So that means that 2 is the current that passes through everything. So there's 2 amps that is here, and there's 2 amps that goes through this one, and there's 2 amps that goes through that one. Once I have that, I can say V1 is equal to I times R1, and that's going to be 2 times 4, which gives me 8, okay? So it's a little progression of equivalent resistance, find the total, and then use V equals IR multiple times as needed to find the different amounts, okay? Any questions, anything? We're done. We'll do parallel next week and do some example problems, et cetera, et cetera. Goodbye. Enjoy the sunshine, and don't fall out of bed. Ever. It's not good. And don't sniff. Sniffing's bad too. No sniffing.